Hello everyone, welcome to this session. In the last session, we have talked about the bias and variance, which are the major components of the prediction error. So in this session, we will go deeper into this topic and we will analyze the relation between bias and variance. So in one sentence, the bias and variance have a trade-off relation. So ideally, we want a model that have both low bias and low variance, right? So, but in reality, in many cases, it's difficult to achieve that. So because that if we decrease the variance, the bias increase. So if we decrease the bias, the variance increase, right? So these two have this kind of relation. Let's have an example. So for example, a model is overfitted. So how about its bias and variance? So the bias is low, right? Because often we measure the bias considering the training data. So an overfitted model fits very well considering the training data. So the bias is low, but the variance is high. So if we provide new data and it will predict them poorly. Right? So this is one example. Low bias, high variance level. Normally, we want to have a good balance between the bias and variance so as to minimize the total error. So let's see this figure. When the algorithm complexity grows, so the machine learning model becomes more complex, so often the bias will decrease. But meanwhile, the variance increase. So we don't want this one, we don't want this one. What we want is consider the minimum total error, right? So we want here, optimal balance. So optimal balance often is not overfit or underfit. So we can see this is the underfitting zone, this is overfitting zone. So we want neither of them. Instead, we want the middle to get a good balance between the bias and variance. So now let's see some examples. So let's see, these are the blue dots, blue circles are the data. So let's consider this blue curve is a true mapping, right? True mapping. So clearly the relation is not linear, but if I use linear regression, then we can find this is a result. So we can see it's really not good. And for the test data, we can see that a linear fitting also not good. So a high bias fitting, we can see that has a high prediction errors, both in terms of the training data and the test data. So it's underfitting, right? So how about high variance fitting? As we can see this figure, this is a true mapping. And here I use a high order polynomial model to fit this. And we can see, considering the training set, the prediction error is very low, right? Fit very well. However, when we see the test set is different, and we can see that using this model, many of the points are fitted very bad. So in the test set, the high error exists. So when we see a low prediction error on the training set, but high error on the test set, so now that we can know this model is highly likely to be overfitting. So we can see it's high variance fitting. So for generalization, we have mentioned it before, and now we can give it a formal definition. So generalization is talking about when I use data, right? That is not in the training data, right? The new data. How well is the machine learning model? So this is generalization. So normally good machine learning models generalize well from the training data to any data in the problem domain. So for example, the good fitting we have shown before, this and this in the last session, right? So we can consider it fit well with the training data and it generalize well with more data. So we neither want underfitting one or overfitting one. So what we want is the good balance between bias and variance. So for example, still for this data, I use not linear, not cubic, I use a quadratic. So this looks much better, consider the the training set and the test set, right? So we can see a good fitting model has no prediction errors on the training set and test set. So in this case, we can think, okay, this is a good model, right? So that's all for the bias and the variance and their trade-off. So thank you very much. Bye-bye.